You'd think going back to the moon would be easy now, right? You're carrying a supercomputer in your pocket, you've got global navigation, high-speed internet, AI, all of it. And yet, the last time a human walked on the moon was 1972. That gap, more than 50 years, should instantly bother you. If the tech got so much better, why does the mission look harder, not easier? But before we continue, please subscribe to the channel to give your support. Let's continue. The first thing to understand is this. The tech that exploded on Earth is not the tech that really limits you in space. During Apollo, the guidance computer on the spacecraft ran at roughly 1 megahertz, with memory in the kilobyte range. That is weaker than the cheapest smartphone you can buy today. Your phone is around 1,000,000 times more powerful in raw operations per second than the computer that flew Apollo 11 to the moon and back. But that computer was never the main bottleneck. The bottleneck was everything around it. The rocket, the fuel, the life support, the mass you had to push uphill. So here's the key question. If computers got 1,000,000 times better, but rockets did not get 1,000,000 times more efficient, where do you think the real difficulty still lives? It lives in the same place it did in 1969, in gravity, distance, and energy. And none of those care about your new processor. The moon is still about 384,400 kilometers away from Earth. That's about 239,000 miles. It is roughly 30 Earth diameters away. That number has not changed, and to cross that distance, you still have to do the same basic job Apollo did. First, you need to get into low Earth orbit. That means pushing a rocket to a speed of almost 8 kilometers per second, around 18,000 miles per hour. At that speed, you are basically falling around the Earth, not back down to it. Then, from that parking orbit, you have to fire the engines again, add several more kilometers per second of speed, and stretch your orbit out until it intersects the moon's path. In simple terms, you need a huge amount of energy just to reach space, and then another big push to reach the moon. Physics sets that price. Computers can help you fly closer to the edge, shave small margins, optimize trajectories a bit, but they do not rewrite gravity. You can't software update your way out of the fuel you need. So when people say, we have better tech now, why is this hard? The answer is because the universe never changed the rules. You are still trying to throw tens of tons of hardware off a planet and then fly it across a 400,000 kilometer gap and then land it safely on an airless rock. Now in Apollo, the way NASA dealt with this was by making the mission as short and tight as possible. Apollo 11 lasted about 8 days and a few hours from launch to splashdown. The plan was go fast, stay on the surface for just over 2 hours on the first mission, grab samples, run a few experiments, get back in the lander, launch, dock, and come home. It was a sprint. Everything was tuned around that. The spacecraft, the consumables, the training, even the messaging. We will go there, prove we can do it, and return. Compare that to what Artemis-type missions are aiming for. You're not talking about an 8-day round trip anymore. You're looking at closer to 30 days total, including almost a week actually on the lunar surface. That means the spacecraft has to keep people alive for almost 4 times longer in deep space and on the moon. Life support has to run longer. Food, water, oxygen, power, all have to be stocked, stored, and managed for a month, not a week. The longer you stay, the more you have to bring. And every extra kilogram of supplies makes the rocket bigger, the engineering harder, and the cost higher. So the mission profile changed from a sprint to something closer to a small expedition. That alone takes the old Apollo difficulty and multiplies it. And that leads into the next shift, which is even bigger. Apollo asked a simple question. Can we land people on the moon one time and bring them home without killing them? Artemis asks, can we go to a much tougher region of the moon, operate there for days, build up infrastructure piece by piece, and keep doing that again and again without the whole system collapsing under cost and risk? In other words, Apollo was, can we visit? Artemis is, can we start living there, at least in short bursts? Visiting is one thing. You can tolerate more risk, you can accept more unknowns, you can burn more hardware for a one-off achievement. Starting to live there, even at the level of repeated short stays, pulls in a different world. You need repeatable logistics. You need standard hardware that can be repaired, not just thrown away. You need plans for resupply missions, backup missions, robotic support. You need to think about where power comes from over years, not days. It turns from a race into an early phase of building a tiny remote outpost. And this is where the human side kicks in and quietly makes things even harder. In the 1960s, people inside NASA openly talked about the chance of losing a crew. The astronauts, the engineers, all knew they were pushing limits with a level of risk that would never be accepted for a normal transport system. There were serious estimates that the chance of losing Apollo 11 was not small, and that if it happened, it would happen live in front of the entire planet. That was the mood of the time. Beat the Soviet Union, accept the risk. Now, look at what you expect today. You fly on commercial airliners with the assumption that you will land safely every time. You watch rocket launches with live social media commentary, and you expect that if something looks even slightly off, there will be huge investigations, hearings, resignations. The tolerance for losing a crew has dropped massively. People talk about acceptable risk, but in practice, there is almost no room for a high chance of death on a flagship mission. To hit that new safety bar, the system has to grow more complex. You need multiple independent ways to abort during launch. You need escape systems that can pull a capsule away from a failing rocket. You need fault-tolerant computers with triple redundancy. You need life support systems that can survive multiple failures. You need detailed probabilistic risk assessments that look at thousands of possible failure chains and force redesigns whenever the numbers are not good enough. Every one of those safety layers adds mass, cost, engineering time, and testing. You get safer, but you also get slower and heavier. That's the paradox. Your technology gets more advanced, but your standards also get stricter, so the net difficulty does not drop, it rises. You are trying to reach the same moon across the same distance with missions that are longer, goals that are bigger, and the safety bar that is much higher. So here's the uncomfortable question that sets up the next problem. If just changing the mission profile and raising the safety standard already makes things this hard, what happens when you realize that the one rocket that could throw enormous payloads straight to the moon, the Saturn V, no longer exists at all, and you have to rebuild that capability in a completely new way? Here's the next hard truth. The one rocket that could throw enormous chunks of hardware straight to the moon does not exist anymore. The Saturn VII, the giant from the Apollo era, is gone. During Apollo, it could push about 140 tons into low Earth orbit. That's about 140,000 kilograms, around 310,000 pounds. And it could send about 43 tons, so around 95,000 to 100,000 pounds, onto a path toward the moon. At liftoff, it produced roughly 34 million newtons of thrust, around 7.5 million pounds of force, more than enough to shake buildings kilometers away. But every one of those rockets either flew or was turned into a museum piece. The production lines are gone, the suppliers are gone, the factories that welded those tanks and built those engines were shut down or repurposed decades ago. The engineers and technicians who could build one by memory either retired or died. There is no warehouse with spare Saturn VII stages sitting under a tarp. So when someone says, "We did it with Saturn VII, why not just roll another one out?" the answer is simple. There are none left to roll. So maybe you say, fine, just build a new big rocket. We have one now, right? The Space Launch System? Isn't that the same thing? This is where the story gets tight. Space Launch System Block 1, the version that flew Artemis 1, is absolutely powerful. It can lift around 95 tons to low Earth orbit, about 95,000 kilograms, and more than 27 tons, so over 60,000 pounds, onto a translunar trajectory, depending on configuration. That translunar number is in the same ballpark as what Saturn VII could send toward the moon. So on paper, you might think, problem solved, we rebuilt the capability. But the details matter. SLS gets there with a very different architecture, a core stage with 4 reused shuttle engines, plus 2 massive solid rocket boosters, plus an upper stage that was never originally designed for this exact job. The performance margins are tighter than Saturn VII enjoyed. That means you have less spare capacity to soak up unexpected mass growth, less fuel to cover last-second trajectory changes, less room for error in stage performance. To make everything work, you lean harder on precision staging, upper stage burns, and complex mission designs like doing more of the push once you're already in space instead of brute forcing more mass off the pad. The physics bill is the same, but you're paying it with a more intricate financial plan. Even if you somehow match Saturn VII exactly in raw numbers, you hit another problem that is much harder to see from the outside. You can open all the old drawings, all the old documents, you can have the complete set of Saturn VII blueprints scanned at high resolution, and you still do not have what really made it work. The tacit knowledge in people's heads, the technicians who knew exactly how an F1 engine turbo pump should sound on a test stand, the welders who knew when a tank weld looked wrong before the sensors did, the test engineers who knew which vibration meant normal and which meant shut it down now. None of that lives in a diagram. You can train a new generation, but they start almost from zero on those specific systems. They have to relearn every quirk with new hardware, new tools, new materials. That takes years of ground tests, failures, rework, and incremental experience, and you can't shortcut it by reading a manual. So when you hear, "We already knew how to build Saturn V," understand that most of that know-how was human skill, built up over thousands of hours on the job, and you can't just flip a switch and recreate that workforce in 2026. Let's say you somehow did recover every procedure and every trick. There is still a huge block in the way. The old Apollo hardware would not pass today's safety and reliability standards. If you tried to literally rebuild a Saturn V and an Apollo capsule with the same design, you would run straight into modern human rating rules. The electronics were not designed with today's levels of redundancy and fault tolerance. Materials that were acceptable then might not meet current fracture, fire, or toxicity limits. Many valves, seals, and wiring approaches would fail today's certification process. So you would be forced to start swapping things. New computers, new avionics, new sensors, new materials in tanks and pipes. Each small change means new tests, new analysis, new failure modes to study. After a few years of that, the rocket you think you rebuilt as Saturn V is actually a new vehicle that just looks similar on the outside. Now you have to qualify this new version as if it were brand new, including full test campaigns and a slow ramp up in confidence. Instead of saving time, trying to resurrect an old design can trap you in a long, expensive modernization process. And all of this sits on top of one more harsh reality. Rockets this big are a niche, high-risk business. Vehicles in the Saturn V or SLS class are not like cars or commercial airplanes. You're not building thousands of them and flying them every day. You might build a handful per decade. Each one is the size of a skyscraper laid on its side, with millions of parts that all need to work correctly within milliseconds, under huge vibration and temperature swings. Because the flight rate is low, every launch is almost a prototype test. You don't get to learn from hundreds of flights per year. You get one, maybe two, and they are all carrying extremely expensive payloads or eventually human crews. That makes every change high stakes. You can't easily iterate in production the way commercial tech companies do. You're forced into a conservative, slow, heavily tested approach. And still, your statistics on reliability grow slowly because you don't have many data points. So when you put this whole picture together, you see why the absence of Saturn V is not just nostalgia, it's a real technical gap. You lost the one proven Moon-class rocket. You replaced it with a new system where margins are tighter, complexity is higher, and experience is thinner. You work under stricter safety standards with lower flight rates and much less tolerance for failure. And yet, you still have to throw tens of tons of hardware toward the moon, on time and on budget. That's the pressure cooker the new lunar program sits in, and it raises the next question. If just building and flying the rocket is this hard, what happens when you also change the landing site to one of the most hostile, badly lit, rough regions on the entire moon and tell astronauts to work there for days at a time? Here's a detail most people miss. The places Apollo landed were the easy parts of the moon. You're talking about big, relatively flat lava plains near the lunar equator, places like Mare Tranquillitatis, where Apollo 11 touched down. Those regions are huge basalt seas, hundreds of kilometers across, with gentle slopes and long periods of sunlight. For a pilot trying to land a fragile lunar module on its first try, that matters a lot. The sun climbs high in the sky there, shadows are short, the ground is mostly smooth at the scale of the lander's footprint, and the guidance system can work with a wide area that is good enough. So when you watch Apollo footage, it's easy to underestimate how carefully they pick those sites and how much they bias towards safety, lighting, and simplicity. The first human landing was on a relatively open plane with decent visibility and a comfortable buffer in every direction. That was the right choice for a first attempt. The question now is, what happens when you stop aiming for the easy planes and instead aim straight at the roughest, darkest, coldest real estate on the moon, near the South Pole? Artemis 3 is targeting the South Polar region, near craters where the sun barely clears the horizon. The moon's axis is tilted only about 1.5 degrees relative to its orbit around the sun, compared to Earth's tilt of about 23.5 degrees. That tiny tilt means that near the poles, sunlight just skims across the landscape. Peaks and crater rims can sit in near continuous daylight, while the crater floors right next to them never see the sun at all. That produces extreme contrast. You get sunlit ridges that are bright and relatively warm right next to permanently shadowed regions where the temperature can sit between about 40 and 110 Kelvin. That's roughly minus 233 degrees Celsius, or down to about minus 387 to minus 261 degrees Fahrenheit. Those are some of the coldest places in the entire inner solar system. For a human in a bulky suit trying to judge distance and depth in a scene where half the view is blinding and the other half is black, that's not Apollo 2.0. That's a different level of difficulty. Sensors on the lander and on rovers have the same problem. Cameras must handle huge brightness differences in one frame. Thermal systems must cope with hardware that may have one side in constant sun and the other radiating heat into deep shadow. The suit has to keep your body near room temperature while parts of the outside are facing conditions colder than Pluto's average temperature. So why go somewhere this hostile at all? Why not keep landing on safer planes closer to the equator? The short answer is water. Those permanently shadowed regions, the crater floors that never see direct sunlight, are cold traps. Any water molecules that wander in, from comets, micrometeorites, or interactions between the surface and the solar wind, freeze out and stay there for very long periods. Over billions of years, that builds up deposits of water ice mixed into the regolith. Missions like Clementine, Lunar Prospect, Chandrayaan-1, LRO, and LC-CROSS have all contributed evidence that the polar regions, especially the South Pole, host significant water ice in these shadows. In the Cabeus crater, LC-CROSS data suggests several percent of the regolith by mass is volatiles, including water. That's why Artemis is going there. Water is not just for drinking. You can split it into oxygen for breathing and hydrogen for rocket fuel. You can use it for radiation shielding and thermal control. If you want any kind of long-term lunar presence, ice is essentially local energy and life support stored in the ground. But the very thing you need to reach, those dark, cold traps, is what makes the environment harder. You're trying to operate right at the interface between brutally cold shadows and harsh sunlight. Hardware has to work across a huge temperature range, from maybe minus 200 degrees Celsius in a shadow up to over 100 degrees Celsius in sunlit areas. That's about minus 328 degrees Fahrenheit to plus 212 degrees Fahrenheit, depending on exact location and surface properties. Lubricants, batteries, wiring insulation all have to tolerate that without failing. A rover wheel rolling into light into shadow can experience a temperature drop of more than 200 degrees in a short distance. So then you get to the next problem. If the lighting and temperature are that extreme on the ground, what does that do to the actual landing? At equatorial sites, the sun gets fairly high overhead during the day. That gives you a broad set of possible landing times, and it keeps shadows relatively short. For Apollo, that meant you could pick a landing time that balanced visibility and thermal conditions without slicing your launch window too narrowly. Near the South Pole, the geometry is completely different. The sun hovers just above the horizon, always at a low angle, so every rock and every ridge throw it a long shadow. A boulder 10 meters across can cast a shadow hundreds of meters long. For a lander using cameras and LiDAR to find a safe spot, long, deep shadows hide hazards and confuse the sensors. For the astronauts stepping off the ladder, the surface can look like a mix of blinding reflection and black pits. Because the sun's path is so shallow, good lighting only happens at certain times. You want an angle where the terrain is visible, but you also need consistent power from solar arrays on the lander, and you may want line of sight to Earth or relay satellites. That pins your landing to specific days, even specific hours, when everything lines up. Miss that window from Earth because of a technical issue or bad weather at the launch site, and you might have to wait weeks or months for the next one. The launch window shrinks, the mission planning becomes more rigid, and the overall risk from delays and reschedules grows. And all that still ignores the most basic question. What does the ground actually look like where you're trying to put the lander's legs down? The South Pole region is not a flat parking lot. It's packed with overlapping craters, ridges, and slopes at many scales. High-resolution mapping from lunar orbit, especially from LRO, has given us digital elevation models and illumination maps, but those are still built from orbit, not from detailed surveys on the ground. When you design a human lander with a footprint around 15 to 20 meters across, roughly 50 to 65 feet, and a high center of mass, you really want the local slope under the landing legs to be under about 10 degrees. Go steeper and you start increasing the risk that the whole vehicle could tip or slide, especially if one leg lands on a rock or in a small crater. Combine that with poorly mapped small-scale hazards, like half-meter to 1-meter blocks, dust that can hide depressions, and lighting that throws long shadows over everything, and the landing problem becomes very tight. The guidance system has to read the terrain in real time, compare it to orbital maps, spot hazards, and still commit to a touchdown point before the fuel runs out. There is no atmosphere for parachutes. Everything is rocket thrust and precise navigation. A mistake of even a few meters on a bad slope could mean a damaged lander or a mission failure. So now, instead of dropping onto a broad, sunlit plain near the equator for a few hours of work, you're sending a tall, heavy lander into rough polar terrain, with narrow lighting windows, extreme temperature swings, and the target zone shaped by where the ice might be. That choice is deliberate because the science and the resources at the South Pole are that valuable, but it also means the surface phase of the mission is going to be much more demanding than Apollo ever was. And that leads straight into the next layer of difficulty. If the terrain and environment are this harsh, what happens when you stop doing quick flag-planting walks and start packing days of real field science, drilling, and exploration into that same environment? So now you're at the South Pole in your head. Rough terrain, narrow lighting, brutal cold. The next question is, what are you actually going to do there, and how does that change the whole game compared to Apollo? First, look at the raw time outside. On Apollo 11, Armstrong and Aldrin were on the surface for about 21.5 hours total, but only around 2.5 hours of that was outside in one spacewalk. The later missions stretched this. Apollo 17 had roughly 3 days on the surface and multiple EVAs, but you're still talking tens of hours outside in total, not days and days for a single mission. Artemis 3 is planned very differently. You're looking at roughly 4 spacewalks spread over almost a week on the surface, with crews going out again and again in that polar environment. That's close to an order of magnitude jump in surface operations compared to Apollo 11's first landing, and still a big step up even from the later Apollos. More time outside means more wear on the suits, more cumulative exposure to dust, more chances for a seal to clog or a joint to degrade. The life support backpack, which has to manage oxygen, carbon dioxide removal, and temperature in that suit, has to work again and again over multiple long EVAs, not just one short demo. Every time you cycle an airlock, you pump dust, temperature swings, and mechanical stress through your systems. The more often you go out, the more ways there are for a small problem to appear and grow. But just spending longer outside is only the first step. The bigger shift is what you're doing with that time. Apollo astronauts collected samples and did basic field geology, but the core mission was still prove we can land, prove we can move around a bit, grab representative rocks, set up some relatively simple experiments, and then get out. Now the goal is to treat the South Pole like a serious field site. That means systematic traverses, planned routes across multiple locations, core drilling into the polar regolith to get vertical profiles, mapping where composition changes with depth, mapping where volatile solids such as water ice and other trapped compounds are concentrated. You're also trying to measure how heat flows through that near-surface layer, which tells you about the subsurface structure and long-term thermal history. That requires instruments that sit on or in the ground for extended periods, not just hands on rocks and quick photos. So the crew is not just walking around, they're executing a tight, science-heavy plan with specific targets, sampling protocols, and instrument deployments that need accuracy, not just enthusiasm. That leads straight into the next problem. How do you run something like a proper lab in conditions like that? The moon's gravity at the surface is about 1.62 meters per second squared, roughly 1/6 of Earth's, or about 0.17 g. You're working in that partial gravity while wearing a pressurized suit with thick gloves that reduce your finger dexterity. Tools feel lighter, but they also don't fall the same, and your sense of balance is different. Fine motor control is harder through that suit, and every motion is slower because you're constantly managing your center of mass so you don't trip. Now, stack on lunar dust. Regolith at the surface has sharp, jagged grains, not rounded like sand on Earth, and it tends to cling electrostatically to surfaces, including suit fabric, visors, connectors, and tools. Once you bring samples into a habitat or a mobile lab, you have to control cross-contamination. Both ways. You don't want your biology or chemistry experiments flooded with dust from the airlock every time someone comes back in, and you don't want lab powders and residues migrating out into life support filters. So, sample handling procedures that are routine in an Earth lab, picking up small chips, pouring powders, pipetting liquids, become much more complicated at 0.17 g inside a small, sealed environment, with people in undersuits and equipment bolted down. Instruments have to be designed or adapted so they can be calibrated and serviced in that partial gravity, with limited access and limited spare parts. Then, whatever you do on the surface, you have to get the data home. During Apollo, you saw grainy TV, a few channels of audio, and relatively modest telemetry. The data flow was limited by the technology and by what you were trying to do. Now, Artemis missions will be pushing a data stream that looks completely different. Think high-resolution terrain mapping, detailed video from helmet cameras and external cameras, instrument data from multiple science payloads, plus full life support telemetry, suit status, habitat health, and navigation data from rovers and landers all at once. That's gigabytes of data over a mission, not a handful of TV channels. On the ground, you're not just listening to a few voice loops and watching a single black and white feed. You're running a kind of distributed control room for a small polar outpost, with teams monitoring different instruments, different systems, and different risks all at once. Every new data channel is useful, but it also adds complexity to planning and operations, because someone has to process it, interpret it, and react to it in real time. And you can't just throw hardware at the problem without thinking about mass. In Apollo, there was already tight mass discipline, but they could sometimes fly a bit of spare capability just to prove they could. In a modern lunar program with strict budget and performance margins, every kilogram has to justify its heat. That means if you want a seismometer, or a mass spectrometer, or a neutron detector, or a radiometer, you have to show clearly what science question it answers, and why that answer is worth the cost, the complexity, and the risk. Precision science instruments often want stable temperatures, stable mounting, careful alignment, and good isolation from vibrations. That's hard to guarantee when everything is either on a lander that just fired engines in dust, or on a surface where astronauts are moving around and rovers are driving nearby. Some experiments need long integration times, which means you must keep them alive and powered across the harsh polar day and night cycles. Others want samples returned to Earth in known conditions, which demands careful packaging, tracking, and storage in that 0.16 g environment, from collection all the way to splashdown. So you end up in this situation. The science goals are higher, the surface stays are longer, the environment is harsher, and the operational complexity explodes compared to a quick flag-planting mission. You're trying to turn the South Pole from place we visited once to place we can treat as a serious laboratory, and you're doing it with suits, systems, and people pushed close to their limits. And that raises the next pressure point. If the work on the surface and the science load are this intense, what happens to the crew when you also stretch the whole mission from about a week, like early Apollo, to roughly a month in deep space and on the moon, with their bodies and brains taking the hit the whole time? You've already seen how the surface work gets heavier, but there's a deeper problem under all of that. Your body was never built for a month in deep space and on the moon. Apollo 11 was about 8 days, launch to splashdown. Artemis 3 is closer to 30 days, almost 4 times longer. That single change hits everything: life support, health, psychology, and the margin for error. Start with the basics that literally keep you alive. In Apollo, systems only had to run for a bit more than a week, so you could be more wasteful. You could bring more water than you absolutely needed. You could swap out CO2 scrubber cartridges instead of pushing them to the limit. You could store food for a short window and not worry too much about long-term freshness. For Artemis, the same core systems have to hold up for about a month in deep space and at the South Pole, with no chance to open a window or grab a spare from a warehouse. Carbon dioxide scrubbers have to keep pulling CO2 out of the air day after day, without clogging or failing. Water recycling has to work well enough that you're not constantly burning fuel just to ship new water from Earth. Food storage has to keep meals safe and usable for the whole mission under changing temperatures and vibration. Waste management can't be an afterthought, because if that system fails, you can contaminate the cabin air, stress the crew, and make simple hygiene a serious risk. When you stretch from 8 days to 30, you're giving every tiny weakness 3 or 4 times as long to show up and turn into a real problem. Then there's the invisible environment outside the hull. Once you leave Earth's magnetic field, you're exposed to a constant rain of galactic cosmic rays plus random solar particle events. On a roughly 30-day mission, your total radiation dose can climb into the range of several tens of millisieverts. That's not instantly catastrophic, but it's not trivial either, especially when you start adding up multiple missions or thinking about long-term cancer risk. So you have to design the spacecraft and the habitat like you're camping in a place where lightning storms can roll in at any time, not like you're on a calm summer trip. You need denser shielding in the areas where the crew spends the most time. You need a storm shelter, often built near the center of the spacecraft, where water tanks, food stores, or dedicated shielding can surround the crew during a solar event. You need monitoring systems that can pick up changes in the radiation environment fast enough that the crew can drop what they're doing and move to that safe zone. In Apollo, the short mission length and different risk posture meant this was less of a focus. Now it's central. And that's just the environment. Your own body starts working against you too. In microgravity, we know that astronauts lose roughly 1 to 2% of bone density per month without strong exercise and countermeasures. Muscles shrink, the heart adapts to the easier pumping conditions, balance systems shift. On the moon, gravity is about 1/6 of Earth, around 0.17 g. That's better than weightlessness, but we simply don't have long-term human data there yet. We don't fully know how bone and muscle behave over months in 1/6 g or how quickly they recover. That means Artemis crews are not just explorers, they're test subjects. They have to stick to strict exercise routines, using treadmills, resistance machines, and other hardware, both in transit and on the surface, just to slow down physical decline. They need regular medical monitoring, checking heart rate trends, blood pressure, blood markers, and more. Apollo crews could push through 8 days with relatively simple countermeasures. Now you're asking people to work hard, do heavy EVA days, and then keep doing it for weeks in an environment where their bodies are slowly deconditioning in ways we're still measuring. Because missions are getting longer, you can't rely forever on the old strategy of bring a lot and throw away the waste. Apollo could afford to be more open loop. You bring water, you drink it, you dump what's left, and you don't worry about recovering every drop. For a sustained lunar program, and especially for 30-day missions, that doesn't scale. You start pushing toward closed-loop life support, where you try to recover more than 90% of your water, recycle as much as you can from humidity, urine, and gray water, and reuse air by scrubbing and regenerating CO2 systems instead of constantly swapping cartridges. The closer your system gets to being closed, the more it stops behaving like simple plumbing and starts behaving like a small ecosystem. Everything interacts. If a filter clogs, humidity might rise. If humidity rises, condensation might form in places you don't want it. If a sensor drifts, the algorithms might overcorrect. You get complex feedback loops, and keeping that stable for 30 days with humans inside is much harder than just bring extra stuff for 8 days and dump what you used. Eventually, you even start talking about pulling oxygen from lunar regolith or using local water, and that adds whole new layers of machinery and risk on top. Now think about what happens if someone gets sick or hurt in that environment. During Apollo, you had almost continuous voice contact with Earth, and the time to get home was relatively short. You still had risk, but you had more of a "we can get back in days" mindset. For a South Pole mission, your communications may be routed through relay satellites, you may have coverage gaps, and you're farther in terms of operational complexity from a quick emergency return. You can't treat the crew like passengers next to an emergency room. They have to be more like a small expedition team in a remote polar station. So they need deeper medical training. Someone on board has to be able to do more than basic first aid. They need to handle fractures, serious cuts, infections, maybe even minor procedures, with only the tools on board and guidance from Earth that might be delayed or interrupted. You need more diagnostics packed into a small volume, compact ultrasound, point-of-care lab tests, smart monitoring devices. You need treatment plans that are designed around the assumption that evacuation is difficult or temporarily impossible. That's a completely different level of autonomy compared to if anything really bad happens, we're home in days and the hospital takes over. When you stretch from 8 days to 30, you're giving every tiny weakness 3 or 4 times as long to show up and turn into a real problem. Then there's the invisible environment outside the hole. You now have to land, and that is getting much harder than it was in Apollo. Back then, landings were basically a mix of human eyes, a radar altimeter, and a relatively simple guidance computer. The computer got you in the right general area, the radar told you how high you were and how fast you were falling, and the astronauts looked out the window and made the final call. On Apollo 11, Armstrong famously took over manual control because the computer was guiding them toward a boulder field. He flew the lunar module sideways, burned extra fuel, and set down in a safer spot. That worked because he had a broadly flat Mari plane, good lighting near the equator, and a bit of hover fuel in reserve to hunt for a landing site. So ask yourself, would that same eyeball plus radar approach work if the ground is full of cliffs, deep shadows, and small patches of safe terrain? That's the situation near the South Pole, and it changes the whole landing problem. For Artemis, you may need to touch down within a few hundred meters of a very specific ridge or crater rim. You want a spot that gets near continuous sunlight for power, is close to interesting science targets, and still meets all the slope and hazard limits. That's not a big open plain. That's more like a narrow zone wrapped around a crater edge. To hit that, you can't rely just on a human looking out the window at the last minute. You need terrain relative navigation, where the lander's computer compares what its cameras see to high-resolution maps on board. You need LiDAR or similar sensors that scan the surface and measure distances in 3 dimensions. You need real-time hazard detection that can pick out big rocks, small craters, and steep slopes, and then adjust the landing point automatically. In simple words, the spacecraft has to recognize dangerous terrain on its own and correct for it while it is dropping toward the surface. The crew can still monitor and intervene, but the system has to do a lot more work by itself than Apollo ever did, because the safe zone is smaller and the environment is more hostile. That pushes the complexity of guidance, navigation, and control way up. Now think about fuel. In Apollo, the lander had a bit of hover time to search. On Apollo 11, they had on the order of tens of seconds of fuel left when they finally touched down. That was already tight on a flat mare. At the poles, the best landing sites for power are peaks of eternal light, small high spots that get sunlight for a large fraction of the lunar day. Some of these may only be a few hundred meters across. You're essentially aiming for a small platform, not a wide field. Your propellant budget is set by the rocket equation and the mass you can deliver. You don't suddenly get extra hover time just because guidance got smarter, so your descent profile has to be tuned to hit that small target without spending too long in a fuel-eating hover. If you realize late that the spot you picked is unsafe, you may not have the fuel to move far horizontally and try again. Abort options are tighter. Changing your mind at the last minute is less forgiving because you are operating on a thin edge between safe landing and not enough propellant to climb or divert. So, can better maps help you rescue here? They help a lot, but they don't solve everything. Before Apollo, we had pretty crude global maps of the moon, built from Earth-based telescopes and early orbiters. Now, spacecraft like the Lunar Reconnaissance Orbiter have mapped the surface in very high detail, with topography measured to meter-scale vertical resolution and images down to sub-meter per pixel in key areas. That's a huge improvement, but it's still not the same as a complete, high-resolution map of every boulder and every small hole in your landing ellipse. What actually happens is this. You load orbital digital elevation models and surface images into the lander's navigation system. As you descend, cameras and LiDAR scan the terrain, and onboard software matches what it sees to that map, correcting its position and refining the local hazard picture in real time. You're building the final landing plan on the fly, combining pre-mission data measured in meters with live sensor data that picks up the last-minute details. Any errors in the maps or in the matching process eat directly into your safety margin. You're past the era where within a few kilometers was good enough. You care about where you are within tens of meters. And all of this happens without something you're used to on Earth. There is no lunar GPS network. On Earth, your phone or car talks to a swarm of satellites, does some timing math, and tells you exactly where you are. Around the moon, you don't have that. Navigation is a stack of inertial measurement units, which measure accelerations and rotation rates, plus star trackers that look at the sky and fix your attitude, plus occasional fixes from radio and optical tracking to orbiting spacecraft or Earth. Once you're near the surface, you add terrain features as landmarks that the software can lock onto. Rovers and astronauts on the ground have a similar problem. Every meter you drive or walk has to be tracked by dead reckoning and cross-checked against maps and line-of-sight references. Small errors in distance and direction can add up over time, especially in 1/6 G, where your gait and vehicle handling are different. If the navigation software glitches, you can't just stop and load a map app on your phone. You need robust, redundant systems that keep working even if one sensor fails or one algorithm starts to drift. So now the landing looks like this. You're dropping toward a badly lit, rough surface, aiming for a very small safe zone with fuel margins that give you little time to hesitate, using a navigation system that has to fuse orbital maps, live sensor data, and inertial tracking perfectly, without the safety net of GPS. The crew is strapped on top of that, trusting that the software and hardware beneath them will not misread a shadow as a safe patch or a slope as flat ground. And that brings up the next nasty layer you haven't even really tackled yet. Even if you land exactly where you want, on the perfect spot, every engine burn and every step kicks up something that sticks to everything, grinds into hardware, and threatens the crew's health. Tiny grains of lunar dust. You can't escape. So let's talk about the thing that quietly makes all of this worse. The moon is covered in a layer of dust and crushed rock that behaves like a weapon against everything you bring there, including you. It looks harmless in photos, just gray powder, but at the microscopic level, it is nothing like beach sand. On Earth, wind and water grind sand grains down, round off their edges, polish them. On the moon, there is no air, no liquid water, and impacts from micrometeorites and larger rocks shatter material instead of smoothing it. The result is lunar regolith, particles that are jagged, sharp, and full of glassy fragments. A lot of those grains are around 10 micrometers across, so smaller than the thickness of a human hair, but shaped more like broken glass than like a smooth bead. Under 1/6 G, when a lander fires its engine or a rover wheel spins, that stuff lifts off the surface easily and does not settle quickly. During Apollo, the suits came back from each EVA absolutely coated. Zippers started to jam, visors picked up scratches, joint bearings wore faster than expected. You're basically spraying the hardware with a cloud of tiny blades. Now add one more effect that doesn't really exist for you on Earth: acetylostatic charging. The moon's surface sits in the solar wind and UV light from the sun. Around local sunrise and sunset on the moon, UV light and plasma can charge dust grains in the ground differently. Some models and observations suggest that this can levitate dust a few centimeters or more above the surface, forming what people sometimes call a dust atmosphere close to the ground. That means even without an engine firing or a rover driving, you can get dust moving, lifting, and drifting into places you really don't want it. If dust can float or hop like that, it can find its way into radiators, into seals, into hinges, into connectors. A radiator that was supposed to radiate heat into space ends up partly covered by a thin film of dark powder, which changes how well it can cool your systems. A hatch seal that was supposed to stay clean ends up with particles embedded in it. A joint that was supposed to move smoothly starts to grind. Suddenly, thermal control is not just about managing heat, it's also a dust management problem. Every design that opens or closes, rotates or slides has to assume that at some point, lunar dust will try to get inside. Then there's the part that hits the crew directly: health. Those 10 micrometer grains are exactly in the size range that if they get into your lungs, they can reach deep into the respiratory system. On Earth, fine dusts like silica are a known hazard for lung disease. Lunar dust is made of silicates and other materials, fractured and sometimes chemically activated by radiation. Lab work with cells and animal models suggests that lunar-like dust can cause inflammation and oxidative damage. On the moon, under 1/6 G, once dust gets inside a habitat, it may stay suspended in the air for longer because gravity pulls it down less strongly, and air circulation patterns are different in partial gravity. That means the filters in the life support system have to work harder, and any leak in your dust control procedures could turn into a chronic exposure problem. If a suit brings back dust into the airlock and that dust makes its way into the cabin, every breath the crew takes becomes a small risk. You can't just open a window or step outside for fresh air. All the air is recycled, so you need good vacuuming, good filtration, good airflow design, and strict rules about how you move from outside to inside. Apollo crews reported irritation in their eyes and throats from dust after EVAs, and they were only there for days. Now you're talking about stays of a week or more, and in future, maybe months. On the engineering side, Apollo could get away with designing most hardware for a relatively short exposure. A lander did a small number of descents and ascents. A rover drove tens of kilometers at most. Suits were used for a few EVAs and then retired. Nothing had to keep working in that environment for years. Artemis and anything that comes after it is different. Landers, rovers, and habitats are expected to endure repeated visits, many EVAs, possibly multiple missions reusing the same hardware. You're suddenly thinking on the scale of a decade of dust, not a week. That pushes you toward things like deployable covers over sensitive surfaces, wipers on camera lenses and solar panels, seals that shed dust instead of trapping it, bearings that can tolerate abrasion, and materials that don't hold onto particles as easily. You can test ideas in vacuum chambers on Earth. You can fire dust at components. You can cycle temperatures. But in the end, you only really know if your design works when it has survived real lunar dust for a long time. That means part of the early Artemis infrastructure is effectively a long-term dust experiment on everything you fly. There's a twist here that adds both opportunity and complexity. The same regolith that is attacking your hardware is also the main local resource you can actually use. If you want radiation shielding for habitats, one of the most efficient ways to get it is to pile meters of regolith on top of your structure, or to build the walls out of it. If you want to build roads, pads, or walls, you can heat regolith until it centers into a solid, or you can use 3D printing techniques to lay it down layer by layer into blocks and beams. If you want to reduce the amount of material you bring from Earth, the obvious place to look for construction material is the ground you're standing on. So you have this situation where you are forced to handle lunar dust both as a threat and as a resource. You need machines that can dig it, move it, heat it, and process it, while those same grains are trying to grind down their joints, clog their filters, and sandblast their surfaces. Every time you choose to use regolith for shielding or construction, you're committing to exposing your equipment to even more dust. That's necessary if you want long-term bases, but it also means you have to design everything from the start with dust in mind, not as a last-minute add-on. Putting it all together, the South Pole mission architecture is being built on top of a surface that constantly tries to damage your systems and slowly harm the crew. You don't get to choose no dust. You only get to choose how prepared you are when it gets everywhere. And just as you're trying to harden suits, vehicles, and habitats against that, you're also making the rockets and mission architecture more complex, splitting launches, refueling in space, and stitching together many moving parts that all have their own ways to fail. So the next question is, if the environment on the moon is already this hostile and the dust is fighting you every second, what happens when the trip to get there is no longer one big, simple rocket, but a chain of new launch vehicles, refueling steps, and on-orbit tricks, each adding another layer of risk between Earth and the surface? You've seen how just landing and staying on the moon is harder. Now there's another layer. Even getting the crew there is no longer one giant rocket, one stack, one shot. Apollo was basically a straight line. One Saturn V, one command and service module, one lunar module, all built under one program, all launched together. You lit the big rocket, you either made it or you didn't. Fewer interfaces, fewer handoffs. Now look at how a modern moon mission is put together. You've got SLS to launch the crew in Orion. You've got a separate human landing system built by a commercial partner. You may have a gateway station orbiting near the moon as a staging point. You've got cargo landers flown on other rockets, maybe from completely different companies. All of these have to talk to each other, dock with each other, refuel, share power and data, and line up in time. Every connection between two systems is a place where something can fail or just run late. So instead of one rocket, one mission, you're dealing with a small network of vehicles and stations that all have to cooperate. Then you add the multi-launch approach. To reduce risk to the crew and reuse hardware better, you might launch the crew on one rocket and cargo on another. You might pre-position the lander near the moon. You might send fuel separately. Each of those decisions comes with a new branch in the decision tree. What if the cargo launch is delayed, but the crew launch is ready? What if the lander reaches lunar orbit, but one thruster looks suspect? What if a tanker arrives with less propellant than planned? You now have to manage a timeline where every step has its own possible aborts, its own possible replan. You're basically trading a single gigantic leap for a series of smaller leaps. But here's the catch. All of those smaller leaps still have to work for the mission to succeed. If you need 3 perfect launches, 1 perfect refueling, and 1 perfect landing sequence, the overall probability of success is the product of all those individual probabilities. Even if each piece is pretty reliable, the combined chain can get fragile fast. That's why mission planners obsess over single-point failures and loss of mission versus loss of crew events. Every new element you bolt into the plan changes those numbers. Now, look specifically at the human landing system design based on a Starship-class vehicle. To make that work, the plan involves launching the lander, then launching multiple tanker versions of the same rocket, then performing a series of on-orbit refueling operations until the lander's tanks are full enough to go to the moon and back. We have done small-scale propellant transfers in orbit before, but we've never moved hundreds of tons of cryogenic propellant, like liquid methane and liquid oxygen, between large vehicles in microgravity, as a routine operational thing. Cryogenic fluids boil off over time. Valves can freeze, sensors can give bad readings when they get too cold or see bubbles, lines can pick up unexpected temperature gradients. On Earth, you store these liquids in well-controlled tanks, with gravity helping separate vapor and liquid. In orbit, everything floats. Managing that without losing too much propellant and doing it reliably across many tanker flights is a brand new challenge. Any serious problem in the refueling sequence can push a mission back by months because you have to refly tankers, retest systems, or in the worst case, redesign parts of the plumbing. Meanwhile, the SLS rocket carrying the crew is its own beast. It uses a big core stage with 4 high-performance engines and 2 massive 5-segment solid rocket boosters mounted on the sides. Those solids give you a huge amount of thrust at liftoff, much more than the core alone, which you need to throw tens of tons toward the moon. But solid boosters also come with brutal side effects. Once you light them, you can't throttle them down or shut them off. They produce intense acoustic energy, basically an enormous sound and pressure field that batters the launch structure and the vehicle itself. That means the pad has to be built to handle those loads. Deflectors, flame trenches, water deluge systems all have to mitigate vibrations and acoustic shocks, or delicate hardware at the top of the stack can get shaken more than it was designed to survive. The rocket structure has to be stiff enough and damped enough to ride out that environment. Payloads, including life support electronics and crew cabins, sit at the top of a stack that's flexing and ringing while the boosters push at full power. The analysis and testing to prove that everything can handle that is deep and time-consuming. You don't get a free pass because we used shuttle engines or we used solid boosters before. The exact geometry, frequencies, and load paths are different. Add in the fact that solids, by their nature, have different failure behavior than liquid engines. A serious problem in a solid can escalate quickly because you can't just close a valve. So you need a capsule escape system that can pull the crew away in the worst case, and that escape system has to work in the middle of that acoustic and aerodynamic chaos. Every one of those pieces adds another branch to your risk tree. Now, overlay all of that hardware with how we think about risk today. In Apollo, there was risk analysis, but it was cruder and the social expectation was different. Today, you run massive suites of simulations, thousands or millions of runs, where you tweak parameters and see how often things break. You fold in data from previous flights, lab tests, supplier quality stats. You build detailed probabilistic risk assessment models, where every valve, every sensor, every software routine gets some chance of failure assigned to it. And then you see what the combined picture looks like. That sounds like a pure win, and in safety terms it is, but it also means you often get told by your own models that a mission profile you've been working on for years is right on the edge of what is acceptable. Maybe the combined probability of losing a crew over a program is higher than a policy limit. Maybe a specific refueling chain drives the numbers in the wrong direction. When that happens, you don't get to shrug. You have to redesign, add redundancy, change procedures, or slow down the schedule. That can mean scrapping hardware you've already built, rewriting software, or even rethinking mission architecture. So in the modern era, you are stuck in this loop. New rockets with new capabilities, but also new failure modes that have to be understood and mitigated, and the risk culture that will call you out if the math doesn't look good enough. You're trying to move humans through a chain of complex systems that all interact, all carry their own risks, and all live under tight scrutiny. And the moment you put that much complexity and that much risk on the table, another question comes crashing in. Who pays for all of this? Who keeps funding it when costs grow and schedules slip? And how do you hold a program like this together when budgets and changing priorities start pulling on it from every side? Here's the part that quietly decides whether any of this actually happens. Apollo had fuel that Artemis just does not have. In the 1960s, at the peak of the program, NASA was getting around 4 to 4.5% of the entire U.S. federal budget. Today, NASA is sitting around 0.3 to 0.4%, depending on the year. So you're trying to run a more complex, longer, safer, more sustainable moon program, but with roughly 1/10 of the spending weight Apollo enjoyed. That matters because Apollo didn't just pay for rockets and capsules. It paid for armies of engineers, multiple test stands, duplicate hardware, full-scale mock-ups, and very aggressive schedules. The country basically said, whatever this costs, we're doing it, and then stuck with that through the mid-60s. Today, you're arguing over every half billion against schools, healthcare, defense, climate, everything else. The bar for this is worth it is much higher, while the raw fraction of the budget is much lower. Then look at the bill for Artemis itself. NASA's own watchdog, the Office of Inspector General, has estimated that Artemis spending will hit around $93 billion by the mid-2020s, when you add up SLS, Orion, ground systems, and other pieces. That's not future fantasy money. That's already committed development plus the next few years of operations. Every time the schedule slips, that total creeps up. You still have fixed costs, you still have contractors on payroll, and you still have to maintain facilities even if a launch gets pushed back a year. Delays don't just hurt pride, they act like a slow leak in the budget. Artemis 1 slipped, Artemis 2 is slipping, Artemis 3 is sliding further into the late 2020s. Those pushes keep adding operations costs while you're still not actually landing people on the moon. Other programs inside NASA see that and feel squeezed. Planetary missions, Earth-observing satellites, space telescopes all start competing for a smaller slice of what's left after human exploration takes its cut. That fuels backlash because members of Congress who care about Mars probes or climate satellites ask why their priorities are being trimmed to pay for a lunar program that keeps moving its dates. On top of that, look at how short the attention span is compared to the mission timeline. Apollo lived inside a Cold War, beat the Soviets frame. The goal was clear, the enemy was obvious, and presidents, Congress, and the public could see the moon landing as a single symbolic win. Today, you don't have that simple external driver. Administrations change every 4 or 8 years. Priorities swing between back to the moon, on to Mars, asteroid missions, low Earth orbit commercialization, and budget tightening. You're trying to design a 10 to 15-year lunar strategy with hardware that takes a decade to mature inside a system that re-argues its goals every election cycle. One president announces a bold timeline, the next slows it down or shifts focus. The one after that might cut the budget and say, let private companies handle more. Long-term engineering does not like that kind of stop-start, change direction pattern. You can't rebuild a heavy-lift rocket or a lander architecture every time someone new sits in the Oval Office, but you also can't ignore the people who sign the checks. Now, layer in the fact that the moon is no longer a two-player race. During Apollo, the game was basically the US versus the Soviet Union. Today, you have Europe, Japan, India, China, Canada, and a crowd of private companies all aiming hardware at the lunar surface or lunar orbit. Every big choice you make has diplomatic weight. Pick a landing site at the South Pole, other nations notice because that might be near ice deposits they were also eyeing. Choose a specific company as a lander provider, and you're also choosing which country's industry gets a boost, because these companies sit inside national economies. Even things that sound purely technical, like who drives this rover or who provides communications, carry signaling value. Is this a US-led mission with foreign guests, or a genuinely shared project? How do you divide science time? Who gets what data first? Whose flags and logos appear where? That's not engineering, that's space diplomacy, and it's harder than beat the other superpower, because now you're trying to keep dozens of partners aligned, while also competing with some of them in other areas. Behind all of this, there's the constant, uncomfortable question inside NASA and in the science community: what do you not fund so that you can fund this? The agency's budget is not infinite. Money you put into SLS, Orion, landers, and ground systems is money you are not putting into other things, like climate monitoring satellites that track greenhouse gases, or robotic missions to Europa, Titan, or a new generation of space telescopes. That means every major Artemis element has to be defended again and again in budget hearings. Why this lander design? Why this rocket? Why this many flights? Program managers have to show that cutting one piece now will cost more later, or that canceling it would waste sunk investment. That slows decision-making, because nobody wants to approve something that will look like a bad call when the next round of cuts hits. You get reviews on top of reviews, reports on top of reports, because the opportunity cost is real and visible. So the money side doesn't just add noise, it directly shapes what kinds of missions you can fly, how fast you can build, and how bold you're allowed to be. Apollo got a brief blank check backed by a clear story. Artemis is trying to build a sustainable presence with less money, less unity, more partners, and more competition, while every delay feeds critics who say the whole thing is too expensive or too slow. And that brings up the next pressure point. Even if you get Artemis funded and flying, you're not going back to a quiet, empty moon. You're heading into a neighborhood that's already getting busy, with robotic landers, rival national programs, commercial missions, and crowded lunar orbits, all sharing the same small set of safe spots and radio frequencies. So the next question is, what happens when you try to run human landings and long-term operations in that kind of traffic? You'd expect the moon to feel emptier than Earth, but in one important way, it's getting more crowded every year, and that crowding makes human missions harder, not easier for you. Before you send people back, a wave of robots is already going ahead of them. Space agencies and companies are dropping landers and rovers near the South Pole to test landing systems, scout terrain, and hunt for ice. India's Chandrayaan 3, NASA's CLPS landers, commercial missions like Odysseus and Athena, and small prospecting rovers like MAP are all part of this push toward the poles. That sounds perfect at first. More data, better maps, more practice. But every new lander and rover is also a new radio transmitter, a new source of contamination, and a new physical hazard on the surface. You have to coordinate frequencies so robots don't jam each other or your crew's communications. You have to define keep-out zones so that future human missions don't trample carefully preserved science sites. You have to track exactly where every failed or half-working lander is sitting, because your future lander might need to come down in the same general region without hitting someone else's dead hardware. The South Pole stops being a clean slate and starts looking like a construction site with debris already on the ground. Then there's the issue of commercial landers trying hard things and sometimes getting it wrong. A private lander can crash, tip over, or end up in a weird orientation, like Odysseus and Athena both did near the South Polar region, and still be counted as a partial success. For science and engineering, that's valuable. You learn from it. For future human missions, it's a headache. Now you're planning a landing where the surface isn't just rocks and craters. It's also someone else's toppled spacecraft, broken solar panels, loose wiring, and possibly sharp metal or composite fragments scattered over the terrain. So the question becomes, how do you route a human lander into a region that may already contain the wreckage from earlier attempts? You can't just say, stay away from where people have failed, because those spots are often exactly where the ice and interesting geology are. You have to map the wrecks, design approach paths that avoid kicking up dangerous debris, and think through scenarios where a misplaced burn or plume might sandblast an older lander and throw fragments into your path. Robotic failures that look acceptable on paper become very real obstacles when humans are following behind. At the same time, other nations are not waiting for you to finish your plan. China is openly targeting polar regions for its Chang'e missions and future crewed landings, and other agencies are eyeing the same general area for their own goals. The South Pole doesn't have infinite good spots. There are only so many ridges with near-continuous light and easy access to shadowed craters. So you run into questions that sound more like urban planning than rocket science. Who chooses which crater rim for which country? How close can two bases safely be before their radio systems interfere, their dust plumes overlap, or their activities start to contaminate each other's science? If another nation puts a lander or a small outpost right next to a crater you were planning to use for ice prospecting, do you move? Do you share? Do you negotiate resource zones? None of that is a solved problem. The more actors you add, the more you have to coordinate, and the more room there is for straight competition, where each side quietly tries to lock in the best spots first. That doesn't just change headlines, it affects your engineering assumptions about where and how safely you can land and operate. And that's just on the surface. Look up and cis-lunar space, the region around the moon, is also filling up. You already have orbiters mapping the surface, relay satellites for communications, test beds for navigation, and in future you might have fuel deposits and logistics hubs loitering in near rectilinear halo orbits or low lunar orbits. Just like low Earth orbits started to get crowded with satellites and debris, lunar space is slowly heading in the same direction. That means when you send Orion with a crew, you're not threading a clean gravity well. You're flying through a space where other vehicles, both active and dead, are moving. So the operations problem gets harder because you now have to think about traffic management around the moon. You need to plan trajectories that avoid known objects, schedule burns and orbital changes so they don't conflict with other missions, and keep good tracking data so that an aging orbiter doesn't drift into a path you were planning to use. You can't have your crewed spacecraft weaving around someone else's old satellite at the last minute because nobody coordinated. That means more rules, more agreements, and more continuous monitoring of what's actually up there. All of this kills the old Apollo assumption that you're basically alone. Back then, when an Apollo mission went to the moon, there weren't a dozen other active spacecraft in lunar orbit, and there definitely weren't commercial robots hopping around near the landing site. Now you have to assume interference, not isolation. Radio frequencies can overlap. Two missions can want the same relay window. Two landers can be operating in line of sight of each other and accidentally cause crosstalk or glare in instruments. Schedules can collide, where one critical landing passes right through a period when another mission is transmitting at high power or doing a delicate operation. That shift from heroic isolation to busy highway means you're not just designing rockets and landers, you're also designing rule sets, coordination centers, monitoring networks, and enforcement mechanisms. Someone has to decide who gets a particular downlink band at a given time. Someone has to maintain a catalog of every object in lunar orbit. Someone has to mediate when two players want the same crater rim. Highways work because they have lane markings, speed limits, and traffic police. Cis-lunar space will need the same kind of structure, just in orbital mechanics instead of asphalt. And the instant you start talking about lanes, rights of way, and safety zones around bases and landing sites, you crash into the next question that makes going back to the moon harder than it looks. If nobody can own the moon, who owns the ice? Who controls the resource zones? And how do you stop safety rules from turning into quiet land grabs?
You'd think the hardest part of using lunar ice would be digging it up, but there's a problem sitting in front of that. Who actually gets to use it in the first place, and under what rules? The moon is not like a gold rush on Earth. You can't just plant a flag and declare a claim, because the core law that covers space says you're not allowed to. Back in 1967, most major spacefaring nations signed the Outer Space Treaty. One of its key lines says, no nation can claim the moon or other celestial bodies as national territory. No sovereignty, no, this crater is now part of country X. That sounds clear, but the treaty doesn't spell out in detail what happens when you start extracting resources, like water ice or metals, and using them. Are you allowed to dig and keep what you dig, as long as you don't claim the land? Are you allowed to sell it? If you build up a long-term operation around a crater, does that give you any special status? So when you talk about sending Artemis crews to the South Pole to chase ice in shadowed craters, you're not just planning a science mission. You're walking right up to the edge of that legal language and testing what non-appropriation really means in practice. You're saying, we don't own the moon, but we are going to take this local resource and use it. Some countries accept that. Others are more cautious or directly skeptical. That legal tension hangs over every engineering decision about where to go and how to operate. To tighten things up on the US side, you have the Artemis Accords, a set of bilateral agreements the United States has signed with multiple partner countries. In that framework, resource extraction is treated as legal as long as it follows the Outer Space Treaty, and there are norms about things like safety zones around bases and key sites. On paper, this gives you more certainty. If your country signs the accords, you're agreeing on basic rules. You know your partners see mining ice as allowed. You know they accept the concept of carving out protected areas around active operations to reduce conflict and collisions. But not everyone has signed. Big players like China and Russia are outside that framework and are developing their own lunar programs and legal interpretations. That sets up the possibility that you'll end up with at least two different legal cultures operating on the moon. One group says, this is how we do safety zones and resources. Another group says, we don't recognize that. We have our own view. From an engineer's perspective, you just want predictable rules. From a lawyer's perspective, you're staring at a potential clash of legal systems in the same physical space. That's where the idea of safety zones gets touchy.
You, as an engineer or mission planner, want a buffer around the lander, a drill rig, or a habitat so other missions don't blast it with exhaust, hit it with dust, or drive over cables and delicate hardware. You call that a safety zone. You define a radius, maybe a couple of kilometers, maybe less, depending on what you're doing. That sounds completely reasonable for operations. But step back and another question hits. When you draw a line around part of the moon and say, nobody else should operate here without coordination, are you effectively claiming that patch? In practice, if not in name? Lawyers and diplomats worry that safety zones could slowly turn into proto-property lines, especially around the most valuable spots, like crater rims with constant light and access to ice. Engineers just need a defined work area where their equipment and crew are at no risk from somebody else's rocket plume. That tension can turn a simple site selection meeting into a long international argument. A crater rim that looks perfect in your slope and lighting models may be radioactive because someone else considers it theirs in some informal sense. On top of the ownership question, you now have to think about environmental ethics, which Apollo barely had to touch. The ice you want to study in those polar cold traps has been sitting there for millions to billions of years, recording the history of impacts and volatile delivery to the moon. It's not just future rocket fuel, it's also a scientific archive. So how much contamination is acceptable? If you park a lander near a shadowed crater and fire engines, some exhaust will hit the surface. If you drive rovers through a pristine cold trap, you churn the regolith and mix clean layers with disturbed ones. If you melt ice in place to extract water, you permanently alter that deposit. You have to decide, do you stay away from certain areas entirely and treat them as protected science zones? Do you limit how many times you can drill in one spot? Do you force yourself to design trajectories and landing profiles that minimize exhaust into cold traps, even if that makes the mission harder? Unlike Apollo, you can't just say, we'll go anywhere and do anything, science will be fine. Artemis has to factor in planetary protection rules and long-term environmental impact, and those constraints loop back into engineering choices. Now, add one more complication. There is no local enforcement. There's no lunar police force, no zoning board that tells you where you can build, no building inspector who checks your habitat design. Every rule is something negotiated on Earth between nations and companies, codified in treaties, national laws, and contracts. If a company or a country quietly pushes the boundaries, builds just a bit closer to a crater someone else was eyeing, or operates a drill in a way that others think is harmful, you can't send a cop car to shut them down. You're back to diplomacy, sanctions, naming and shaming, or legal cases that move on Earth time, not mission time. That means a lot of the early work on Artemis and its partners isn't welding tanks or testing engines. It's meetings, working groups, draft agreements, and endless wording tweaks about what safety, interference, and resource utilization actually mean. Engineers build schedules around hardware delivery dates, but those schedules can be quietly stretched or blocked by legal uncertainties. If you don't know whether a certain type of mining will be accepted or challenged, it's hard to design equipment and commit billions to build it. So the frontier you're trying to open is constrained not just by mass and fuel, but by laws and norms that are still being hammered out. You need enough legal clarity to justify major investments, but not so rigid a regime that it locks out innovation or turns everything into a territorial fight. Get that balance wrong, and either the program stalls under uncertainty, or you trigger the kind of competition that makes cooperation almost impossible. And right when you see how messy that legal and ethical picture is, you have to remember one more thing. You're not even trying to do all of this as a pure government project anymore. You're leaning hard on commercial partners with their own incentives, their own timelines, and their own investors. So the next question is, what happens when you bolt this fragile legal framework on top of a new space economy, where delays, bankruptcies, and rapid iteration are normal, but your human landing schedule depends on those companies delivering perfectly? Here's another shift that makes this whole thing harder for you. The moon program is no longer one big government machine you control end to end. In Apollo, almost everything flowed through NASA, with contractors building parts, but the architecture, the schedule, and the interfaces were all owned by one customer. Now, Artemis leans heavily on commercial partners for landers, rovers, comms, and cargo, and that adds a different kind of risk on top of the technical risk. A government program can be slow, bureaucratic, and expensive, but it rarely just shuts down because the market turned. A company can. A commercial lander provider can run out of cash, get bought, pivot to another business, or decide that the risk profile is too high for what they're being paid. You're no longer asking, will the engine work? You're also asking, will this company still be around with the same priorities by the time we need them to fly humans? That's market risk sitting directly under your life support chain. You see this most clearly with the human landing system based on a heavy lift vehicle like Starship. NASA's Artemis planning and this vehicle's development are happening in parallel, not in sequence. The rocket is flying test missions. Some go well, some don't. Designs get tweaked, timelines move, cargo manifests, and even surface stay durations get adjusted because the underlying lander is a moving target. You can't wait for the vehicle to be finished before you start planning, because that would delay Artemis by many more years. But planning on something that's still changing means you carry uncertainty all the way into integration. Every big test failure forces you to ask, does this push our human landing date? Do we need a backup? Do we redesign our interfaces? The technical iteration that makes the rocket better over time also kicks your schedule and risk models around. At the same time, you're asking commercial partners to build rovers and surface vehicles for conditions that are far more extreme than anything Apollo dealt with at all. The new lunar terrain vehicles for the South Pole have to survive temperatures from around plus 54 degrees Celsius down to roughly minus 200 degrees Celsius. That's about plus 129 degrees Fahrenheit to minus 328 degrees Fahrenheit. They have to deal with permanent darkness in some areas, very low sun angles in others, and brutal slopes and ridges near crater rims. A Jeep-style rover that worked on the relatively mild equatorial plains won't cut it. You need thermal systems that can keep batteries and electronics alive through long cold spells. You need drive systems that can climb and descend on loose regolith at the edge of steep terrain without tipping a crew or snapping a wheel assembly. You need dust-resistant joints, autonomous navigation smart enough to handle low-angle shadows, and fail-safes that keep the rover useful even if part of it freezes or gets abraded. You're essentially asking companies to build off-road vehicles for the most unforgiving off-road environment you can imagine, and to do it on tight mass budgets. On top of that, you have smaller commercial robots setting the stage in ways that blend science, technology development, and economics. Little prospecting rovers go out to test autonomous navigation on rough ground, to sample regolith, to measure how stable lander plumes and dust clouds really are, and sometimes even to participate in symbolic resource sales, where a company collects a sample and transfers legal ownership of that tiny bit of moon material to NASA as a demonstration of commercial extraction. That's not just engineering, that's the beginning of a market. You're proving that you can provide a service, deliver regolith from this location, or map ice content here, and get paid for it. Science goals, legal interpretation of resource rights, and commercial viability are all tied together. If those robotic missions go well, they de-risk future human operations. If they fail, the technical lessons are still useful, but now contracts, investors, and public expectations are also in the mix. All of this sits on a contract structure that's very different from the old cost-plus world. Many Artemis-related deals are fixed price, milestone-based. That means NASA agrees to pay a set amount if the company hits specific technical milestones: design reviews, hardware delivery, test flights, successful landings. If a company solves problems efficiently, they can profit. If they run into more trouble than expected, they eat some of the overrun. This setup pushes companies to move fast and innovate, which is good for cost and speed in the best case. But it also encourages optimistic timelines and aggressive promises, because winning the contract means convincing everyone you can do it quicker and cheaper than competitors. When reality hits, milestones slip. A lander meant to fly this year moves to next year. A rover that was supposed to be ready for Artemis 3 ends up aligning better with Artemis 4 or V. Every time that happens, the human mission timeline gets yanked around too, because your crewed landings depend on those systems being ready and safe. NASA can't just say we'll launch on schedule anyway if the lander or cargo systems aren't there yet. You get schedule whiplash, driven partly by normal technical learning and partly by commercial risk and contract dynamics that Apollo never had to juggle. Back then, if a subsystem was late, it hurt the schedule, but you weren't also juggling shareholder expectations and commercial launch manifests. So now, instead of a single government stack aimed at a single goal, you have a mixed economy where public and private players are deeply entangled. The upside is more capability, more innovation, and potentially lower costs over the long run. The downside is that your critical path to getting humans onto the moon now runs through companies that can slip, fail, or change direction for reasons that have nothing to do with what's physically possible. And that's still not the end of the invisible complexity. Under all of this hardware and contract structure, there's one more layer that has changed completely since Apollo: the software, the simulations, the cyber side. You're flying missions where millions of lines of code, autonomy algorithms, and digital twins are as critical as the metal, and every extra line of code is one more place something can go wrong. So the next question is, if rockets, landers, and rovers are getting more capable but also more software-driven, how much harder does the mission get when the invisible software stage becomes as complex as the rest of the rocket combined? How do you crash a moon mission without breaking a single bolt? You do it in software. And that's the quiet risk that's exploded since Apollo. You're flying way more code than metal now. Back then, the guidance software for Apollo lived in tens of thousands of handcrafted code, burned into core rope memory. That was already a big deal at the time. Now, if you count the flight software on the spacecraft, the lander and rovers, the ground systems, mission planning tools, analysis pipelines, even the visualization and training sims, you are easily in the millions of lines. Every navigation routine, every sensor driver, every redundancy manager, every user interface, it's all code. More code doesn't just mean more features, it means more ways two modules can interact in a way nobody thought about. A bug that is harmless on its own can become dangerous when it's chained with a timing glitch, a noisy sensor, and an edge case in a state machine. In Apollo, the famous 1201 and 1202 alarms during descent were already enough to almost abort the first landing, and that with a comparatively tiny software stack. Now, multiply the complexity by 100 or more, and you can see why teams obsess over reviews, test harnesses, and code coverage. So here's the blunt question. How do you trust a machine that's basically a flying, stacked software project when a typo, a bad assumption, or a race condition could, in the worst case, kill a crew? On top of that, you're defending against threats Apollo never had to think about. In 1969, nobody was trying to hack a moon mission. The spacecraft were essentially isolated, custom hardware talking to dedicated ground stations. Today, you have networked systems, ground infrastructure that shares networks with other users, and a world where cyber attacks are normal. You're forced to treat every ground-to-space link and every networked subsystem as part of a cybersecurity perimeter. That means encryption on command and telemetry links, authentication on who's allowed to talk to the spacecraft, intrusion detection on the ground side, strict configuration control for any software that ever touches flight systems. None of that gets you 1 meter closer to the moon. It does not reduce fuel use, it does not improve landing accuracy, it's pure defensive overhead, forced by the world you live in. But if you ignore it, you risk someone spoofing commands, jamming links, or injecting bad data into critical systems. So the software stack grows again. More layers, more checks, more complexity. And then, because you're going to the South Pole with patchy lighting and possible communication gaps, you have no choice but to push autonomy much harder. In Apollo, the crew had near-continuous contact and good lighting. The computer helped, but humans could step in and manually pilot the lander. In Artemis-class polar missions, you might not have a perfect, clean, real-time link throughout descent, or while rovers are working behind a crater rim. The machines have to make more decisions themselves. For landers, that means onboard hazard detection and avoidance, terrain relative navigation, real-time trajectory adjustment based on what cameras and LiDAR see. For rovers, it means picking safe paths, avoiding hidden slopes, managing power, deciding when to stop and phone home, all with only occasional ground guidance. For the habitat, it means automatic fault management, switching over pumps, valves, and power routing when something fails, without waiting for a controller on Earth to notice an alarm. That's AI and control theory running in a place where just reboot it and see if it helps is not a casual option. A reboot during landing could mean losing your position solution. A bad autonomy decision could send a rover over a ridge it can't climb back up. A fault handler that triggers at the wrong time could shut down a system that was actually fine, right when the crew needs it. You want the machines to help you by carrying more of the cognitive load, but every extra layer of autonomy is another layer you have to prove will not suddenly help in the wrong way. Before any of that flies, you simulate. And this is another hidden way the mission gets harder. You don't just run a simple trajectory sim and call it a day. You build digital twins of the spacecraft, the lander, the habitat, even the suits. You simulate trajectories, thermal environments, structural loads, dust plumes from engine exhaust, lander plume effects on regolith, human workloads on EVAs, traffic schedules for orbit, worst-case radiation storms, all of it. On the upside, that gives you much better understanding than Apollo ever had. You can spot that a certain landing profile overheats a tank, or that two rovers will get in each other's line of sight, or that a specific EVA plan overloads the crew late in the mission. On the downside, every time you find a new failure mode in simulation, you now feel pressure to design around it. You add a valve here, a sensor there, a software check somewhere else. The design gets safer but also more complicated. You end up iterating not just on hardware, but on models, feeding in new data from tests and early missions, and then watching your risk matrix shift again. So you spiral. More sim, more findings, more mitigation. And the simple problem of flying to the moon turns into a years-long conversation between models and designs. Apollo didn't have that level of simulation power, but in a weird way, that limited how many hypothetical failure chains they had to worry about. You now see more ways things can go wrong, and once you see them, it's very hard to ignore them. All of that leads to one more brutal reality. Getting the software certified to fly with humans is basically its own mission. Flight code has to meet strict standards for requirements traceability, testing, regression coverage, configuration management, and sometimes even formal verification of key pieces. You need to prove, not just hope, that critical functions behave as specified in every allowed state and input combination, or at least in every combination you can reasonably reach. The more integrated your system is, the worse this gets. When the lander talks to the habitat, which talks to the rovers, which talk back through a relay, and all of them share some common libraries or protocols, every change in one place potentially ripples into others. So a small tweak to fix a bug in one module triggers a retest across multiple systems. Regression test suites grow. Simulation farms expand. The schedule for just updating that one bit of code stretches because you can't risk a silent side effect in a corner of the system that only shows up during a contingency. In practice, that means you are running a parallel program just to mature the software. Hardware hangs in clean rooms waiting for the right software build. Astronaut training timelines are tied to when the interfaces stop changing. Ground systems have to stay synced with flight code versions. Delays in the software world become delays in the physical world because you can't separate them anymore. So underneath the metal and the fuel, the invisible rocket stage made of code can make or break the mission. If it's too simple, you can't handle the South Pole and modern safety expectations. If it's too complex, you drown in bugs, certification, and weird edge cases. You're walking a thin line between under-automated and over-fragile. And after you stare at all those layers of tech, from rockets to dust mitigation to autonomy, you hit the one variable that refuses to behave like hardware or software at all: the humans. Their minds, their bodies, their limits. That's the payload that is hardest to model, hardest to certify, and impossible to patch with a software update. Here's the part people always underrate. The hardest thing to send to the moon isn't a rocket stage or a lander. It's a human brain and body that have to keep working under pressure for weeks on an airless rock with no real way out if things go wrong fast. On Apollo, the crews knew the surface part was short. hours to maybe a few days on the later missions. They could mentally frame it as a sprint, hold their breath psychologically, power through the discomfort, then go home. Artemis crews are looking at almost a week on the surface in the South Polar region, inside a roughly 30-day mission. They'll be dealing with long workdays, harsh lighting, temperature swings, dust, and a schedule full of high-stakes tasks, not just sightseeing. On top of that, polar geometry and relay constraints mean communications might not be perfect and continuous every minute, so you get periods where the link isn't as clean or as immediate. That's not just physically hard, that's a human factor stress test. You're asking a small crew to live in a confined volume with no natural sky, no fresh air, limited sleep flexibility, and constant awareness that one serious failure in life support or power could become an emergency. The workload has to be high enough to justify the mission, but not so high that people burn out, lose focus, or start making sloppy mistakes. So psychologists and human factors engineers are in the loop from the beginning, looking at shift patterns, EVA plans, sleep schedules, and even how the habitat interior is laid out. Small things like where you can sit, how much you can personalize a corner, how often you can talk to family, all feed into whether stress stays manageable or quietly builds up. Step outside the habitat and the next pressure point hits you. The suit isn't just clothing, it really is a personal spacecraft wrapped around your body. A modern lunar suit has to handle temperature control, keep you at something close to room temperature while the outside swings between maybe plus 100 degrees Celsius and minus 328 degrees Celsius. That's plus 212 degrees Fahrenheit down to about minus 328 degrees Fahrenheit across different locations. It has to scrub CO2 efficiently, supply oxygen, manage humidity so your visor doesn't fog, maintain pressure so your blood stays liquid, and keep dust out of joints and seals, all while letting you move well enough to climb slopes and handle tools in 1/6 the G. And it has to do all of that at a mass that's still workable. Numbers like 120 to 130 kilograms on Earth, around 260 to 286 pounds, get thrown around as upper targets for a full suit and life support unit. On the moon, that feels lighter because of the lower gravity, but the inertia is still there when you start and stop moving. Compared to the Apollo A7L suits, which were already challenging to work in, you're trying to add better mobility, more robust dust mitigation, more advanced electronics and comms, and extra safety features without turning the astronaut into a walking refrigerator that's too stiff to do precise work. So the suit becomes a major engineering project on its own, with debates about how stiff the joints can be before fatigue sets in, how much range of motion you absolutely need in shoulders and hips to handle polar terrain, and how to make donning and doffing as simple as possible so you don't waste hours and energy just getting ready. While you're wearing that one-person spacecraft, the job list isn't like a simple rock collection run. You're deploying seismometers and other geophysical instruments, drilling cores into the regolith to reach suspected ice layers or ancient deposits, scouting for resource-rich zones, operating or supervising rovers, setting up power systems, checking cables and connectors, maybe assembling or expanding small infrastructure elements like towers or experiments. That's a mix of science, construction, and maintenance. Each of those tasks has steps, decision points, and failure modes. You can't just stack them randomly and hope the crew stays sharp. Cognitive workload analysis becomes as important as fuel margins. Teams have to ask, how many decisions per EVA are we assigning? How many separate procedures are we asking one person to keep in their head? How many times are they switching context between careful science mode and heavy manual work mode? If you overload them, error rates go up. A dropped tool, a misconnected cable, a misread gauge can be more dangerous out there than a small hardware fault. So operations teams build timelines where hard tasks are spaced out, critical steps get double checks, and the crew has short breathing spaces built into the day, even when time is tight. Over all of that, there's a new kind of pressure Apollo never had to deal with: real-time global reaction. In the 1960s and early 1970s, news traveled through TV broadcasts, radio, and newspapers. The audience was huge, but the feedback loop was slow. Now, whatever Artemis crews do will be watched, clipped, and commented on across social media in minutes. A strange noise picked up on a loop, a brief loss of signal, a small correction burn that wasn't fully expected, all of those can become trending topics before the crew even goes to sleep. That doesn't directly change the physics, but it changes the psychological climate. Program managers know that any visible anomaly could trigger a wave of "this is too dangerous" commentary. That feeds back into risk perception on Earth, which can drive more conservative decisions, more delays, more pressure to avoid anything that looks even slightly risky, even when the engineering numbers say it's acceptable. For the crew, knowing that every move is being dissected by millions in real time can add another layer of stress. You have to train them not only to handle the physical mission, but also to mentally detach from the noise and stay focused on the plan. And then there's training itself. Apollo training was intense, no question, but it had a narrower focus. The mission profile was better defined, the surface work set was smaller, and the technology stack simpler. Artemis-era astronauts have to carry a much wider skill set. They still need piloting and spacecraft systems knowledge, but now you pile on deep geology training so they can make smart calls about where to sample and what to prioritize on the fly. You add more systems engineering so they can diagnose and patch problems in a habitat or rover without a huge team walking them through every step. You add maintenance training because hardware is expected to last across multiple missions, not be discarded after one stunt.
On top of that, someone on the crew needs serious medical skills beyond basic first aid to handle emergencies when evacuation is not instant. Everyone needs to be comfortable working with robotics because rovers and maybe small helper bots will be part of daily operations. They're not just passengers using a machine. They're operators and sometimes repair techs. So you end up training for a proto-colony skill profile where a small group has to be able to cover science, engineering, medicine, and construction instead of a narrow visit, plant a flag, leave focus. All of this makes humans the hardest subsystem to design around. You can calculate fuel margins, you can model thermal loads, you can test valves until they fail, but you can't rewrite human sleep cycles, emotional responses, or bone biology with a firmware update. So a lot of the new difficulty in going back to the moon is about designing missions that humans can actually execute safely and repeatably, not just missions that are technically possible on paper. And once you accept that, there's one last twist that pushes the difficulty even higher. You're not just doing this to visit the moon again. You're doing it because the moon is being treated as a test run for something even harder, multi-year missions to Mars. So the next question is, how much extra weight do you load onto an already tough lunar program when you demand that every system, every habit, and every lesson must also prepare you for surviving years away from Earth? So here's the last twist that really answers the whole paradox. You're not treating the moon as the finish line anymore. You're treating it as the warm-up for something a lot worse, Mars. That means you don't get to optimize just for a short lunar mission. You have to design every major system with the next step in mind, even if that makes the current step harder. On Apollo, nobody cared whether the life support system or the habitat concept could scale to 3-year missions at 0.38 G. You just needed it to work for days. Now, when you design life support, habitats, power systems, even simple crew procedures, you're asking, can some version of this scale up to a Mars transit, a Mars surface base, and a return? So a lunar habitat isn't just a cabin, it's a prototype for a Mars module. A water recycling unit isn't just handling a week of waste, it's proving that you can run closed loop for months without poisoning the crew. Every design review has that extra constraint hanging over it. Not just, does this work on the moon, but does this teach us enough and scale well enough to justify itself as a step toward Mars? That hits in situ resource utilization directly. On paper, you could run a lunar program for a while by just hauling everything from Earth: water, oxygen, fuel, construction material. It would be expensive, but for a small number of missions, it's technically possible.
But if Mars is the real goal, ISRU stops being a nice to have and turns into do this or you don't go further. You need to show that you can dig, heat, and process regolith to pull out oxygen and metals. You need to show that you can locate, mine, and purify lunar ice water. You need to show that you can store those products and use them to support crews, and maybe even fuel vehicles. So you start shipping not just landers and habitats, but pilot plants, test reactors that heat regolith and crack oxygen out of metal oxides, small mining units that scrape and haul icy soil from shadowed areas to processing hubs, chemical plants that demonstrate turning water into hydrogen and oxygen for fuel. Each of those adds complexity, mass, and new failure modes to an already tight mission. You're no longer just going back to the moon, you're dragging the early pieces of an off-world industrial system along with you. Because if you don't learn how to use local resources, the Mars plan collapses under its own resupply cost. Once you accept the moon as a rehearsal, your standards for redundancy and autonomy also ratchet up. A lunar mission that is just good enough for a week and relies heavily on constant ground support doesn't buy you much for Mars, where you have long communication delays, limited resupply, and no fast abort. So you start deliberately pushing lunar systems toward Mars-grade robustness, more backup systems, more cross-training so any crew member can cover multiple critical roles, more fail operational requirements, where the system must keep working through certain failures, not just fail safely. That means you might add a second independent air recycling path, even if a single path would technically be enough for a 30-day lunar mission. You might require higher levels of autonomy in power management or fault response than the moon strictly demands. You might train the crew to handle more medical and repair scenarios locally, even though Earth is still relatively close. You are intentionally making the moon mission harder and heavier, because if you don't raise the bar now, you risk discovering lethal gaps when you're already halfway to Mars. Then there's the logistics side. A short lunar program could, in theory, be handled by flying a handful of big missions, accepting high cost per flight, and then standing down. But a sustainable lunar presence and anything that can stretch to Mars needs a backbone. You need a launch cadence you can actually maintain, not a heroic rocket every few years. You need a supply chain for engines, tanks, avionics, and consumables that can support repeated missions without everything turning into a custom one-off. You need maintenance cycles for spacecraft and ground systems, refurbishment plans, spare parts pipelines. If you start producing fuel or oxygen on the moon, you also need an industrial and logistical flow for that. Storage tanks, transfer lines, schedules, inspection routines. The whole thing starts to look less like an expedition and more like a small, distributed industry spread between Earth, lunar orbit, and the surface. And that infrastructure has to be built in a way that can later support Mars missions as well, in terms of launch rate, cost per kilogram, and operational tempo. Standing up that kind of multi-world logistics chain is much harder than just buying a few rockets for a one-off stunt. When you stack all of this on top of the raw physics, the constraints, the safety expectations, and the human limits, the answer to the original question finally snaps into focus. You look at your phone, you look at Apollo's 1 megahertz computer, and you ask, why is going back to the moon harder now? The answer is, you're not really going back at all. Apollo touched the moon for a few days at a time, under extreme risk to win a race. Artemis is trying to turn the moon into the first operational node in a multi-planet civilization. You're trying to learn how to live off Earth's surface, how to run closed-loop systems, how to use local resources, how to keep humans alive and sane under partial gravity and constant radiation, how to coordinate many actors in a shared hostile environment. You're loading that entire agenda onto missions that also have to be safer, more defensible, and more repeatable than Apollo ever was. Touching something once is hard. Building on it is worse. The moon hasn't moved. The distance is the same, the gravity's the same, the basic speed you need to get there is the same. What changed is what you're asking from the mission. You're asking it to be not just a destination, but a foundation. And foundations take more effort, more time, more money, and more patience than the first flag. That's why, even with a supercomputer in your pocket, going back to the moon is harder than going the first time. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.